Hello friends, welcome to lecture number 17 of complex analysis. In this video we are going to prove Taylor's theorem. So what does it say? If a function f of z is analytic at all the points inside a circle C with its center at the point A and radius is r, then at each point z inside C. Suppose this is a circle enclosing a point z, okay, inside C, this is C, and at its point z, this function f of z can be expressed in this form of series, and this is called Taylor's series. So let us prove this. And here let me tell you, this f dash of a represents first order derivative of this function f of z at z is equal to a. Similarly, f double dash a represents second order derivative of f of z at z is equal to a, right? So similarly, this fn of a represents nth order derivative. So hope you have understood this. So now let us prove this. So here let us take any point z inside C, okay, inside C. So let me write here inside C. This C is nothing but a circle, so let me write the word circle here. Inside the circle C, and let us draw a circle C1, let it be C1 with center A and closing the point Z. Suppose this is a circle, this is C, just wait, this is C, and here we have the point Z. Here we have the point Z and its center is suppose at A, and let us draw another circle. This first one is C, and let us draw another circle having same center with the same center, okay, and closing Z, okay. So its center is also A, suppose, and this circle is C1, okay. Let us assume that way. Here this radius is r, this radius is capital R, and this from A to Z, this length is less than r, okay. And let us take a point W on the circle C1, okay. So just what we're going to write here, let W be a point on C1, let W be a point on C1, not inside or outside, it is on C1, okay. Then here you see, let us take 1 by W minus Z. So it can be written as 1 by W minus A minus Z. So if you cancel minus a plus a, then again you're gonna get this, right? So and it can be simplified as here you see, if you take this minus common from these second two terms, okay, then it can be written as minus Z minus A. You can write this way. So hope you have understood this. So now if we take 1 by W minus A common, then what we're gonna have? We're gonna have in the denominator 1 minus Z minus A divided by W minus A, right? So if you multiply this W minus A with this, then again you're gonna get this result, right? So hope you have understood this. So now you see, it also can be written as 1 by W minus Z is equal to 1 by W minus A. It also can be written as, so here you see we have power 1 by this, so it can be written in this way, 1 minus z minus a by w minus a whole to the power minus 1, right? So we're gonna apply the binomial theorem. Okay, so according to that theorem, now you see we can expand 1 minus x whole to the power minus n in this way. 1 plus n x plus n into n minus, sorry, not n minus 1, n plus 1 by 1 into 2 x square plus n into n plus 1 into n plus 2 by 1 into 2 into 3 x cube plus dot 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 and so on, right? So if you compare this one with this, then you're gonna get n is equal to 1, and compare this one with this and this one with x, right? So then what we're gonna get the result. So we're gonna get this just wait. So what we're gonna have, so it's gonna be equal to 1 by w minus a, 1 by w minus a. So 1 plus n, here n is 1 into x, x is this is the x now, z minus a by w minus a, then plus, then again we have n into n plus 1, that is 1 into 1 plus 1 means 1 into 2, and the denominator is again 1 into 2 here, 1 into 2, then x square. So here x square going to be z minus a by w minus a whole square, z minus a by w minus a whole square, and so on. We can continue that way. So now here you see, so let me bring it down, just wait. So what gonna be the next term? Here you see, if you put again here n into n plus 1 into n plus 2, that means 1 into 2 into 3, 1 into 1 plus 1 means 2, 1 into 1 plus 2 means 3, right? Divided by 1 into 2 into 3 again, 1 into 2 into 3 again. X cube is nothing but your z minus a into divided by w minus a whole cube, and so on, right? We can carry that way. So now you see, now let me cut these things. Okay, so hope you have understood how I have applied this. Okay, so here I'm going to write using binomial theorem, right? So here you can see, so these two gonna be cancelled, these two also gonna be cancelled, so this can be written this way. So we can write this way, just this two gone, these two also gone. So this is the result we have got applying binomial theorem. After application of binomial theorem, this is the result we have got, right? Just wait, let me write that way. So that's the result, and here we can write z minus a whole to the power n by w minus a whole to the power n, right? Now what we can do, we can multiply this one with this, it's an every term, right? So then what we gonna have, then it's gonna give you 1 by w minus a plus z minus a divided by, if you multiply these two, that's gonna be w minus a whole square, then here z minus a whole square. If you multiply this one and this one, then it's gonna be z minus, sorry, not z minus, w minus a whole cube, then dot 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 so on, and at the end you're gonna have z minus a whole to the power n divided by w minus a, here n plus 1, right? That's what we're gonna have. This is suppose equation number 1, w minus z is equal to this is equation number 1. Now let me copy this equation number 1, let me go to the new slide. So here is the new slide, this is the equation number 1, and let me take the diagram as well. Okay, let it copy it. So here is the diagram. So here you see z minus a. This is its value is less than w minus a, right? Because you can see this inner circle, the inner circle, this circle inside C, that is C1. Inside C we have C1. This is C1. So this is the center A. You know, Z is inside the circle and W is on the circle. So that's why it is obvious that mod of W minus A, mod of W minus A is greater than mod of Z minus A, right? Because W is far away from A compared to Z from A, right? So that's why we can write Z minus A is less than W minus A, right? So hope you have understood this. And if so, then Z minus A gonna be very smaller than W minus A whole square. Similarly, Z minus A square, that's going to be very less than W minus A whole cube, right? Because here you can see that mod of Z minus A by W minus A, it is already less than 1, right? So if you take the higher powers, it's going to be very less, right? So that's why we can say this series is converging. Therefore so we can say, so the series converges uniformly, hence if it converges, it can it is integrable, right? It is integrable. So remember this condition: if the series is converges uniformly, then it is integrable. Why it is converging, I have already told you the reason. So now you see, let us multiply equation number 1 with f of w. Okay, multiplying both sides by f of w. Okay, multiplying both sides of equation number 1. Let me write of equation number 1 by f of w. Then what we're gonna get? F of w, if you multiply here on the left hand side f of w, then you're gonna have f of w by w minus z. On the right hand side, if you multiply here, then what you're gonna have? F of w by w minus a, right? And similarly, you're gonna have z minus a into f of w by w minus a whole square. And similarly, if you multiply here, then you're gonna get z minus a whole square, f of w by w minus a whole cube, and dot so on. And here you're gonna have, just wait, z minus a whole to the power n f of w by, just wait, f of w by w minus a whole to the power n plus 1. That's what you're gonna have, and dot so on, right? So now let me take a new slide. Let me copy this last step and let me go to a new slide, right? As we have not enough space here, so here this is the new slide I'm taking. Okay, now what we're gonna do, now let us integrating with respect to w. Integrating with respect to w, then what we're gonna get? So here you see, let me copy this series again, just wait. So this is the series. So if we integrate here, then what we have to write here, just wait, there's going to be dw here, then again integrate this one as well, dw, right? Again this is along c1. Okay, we are integrating along c1, so right here c1 dw plus again integrate this, so So here dw plus, so this can be also integrated along c1. So let me just write below here. So here you see, so integrating this along c1, so here dw plus dot 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 so on. That's what we're gonna have, right? So now you see, again I have to take a new slide. So let me copy this one again. Let me go to another slide. Okay, so here you see, okay, just wait, this is the last step we have got. So now let us use Cauchy's integral formula. Okay, so by Cauchy's integral formula, so let me take this as equation number 2. Okay, so we have already discussed about Cauchy's integral formula. Okay, so what's all the previous lectures given in the description box, links are given in the description box. Maybe we have discussed in 14 and 15, maybe we have discussed about Cauchy's integral formula 14, 15, or maybe 16. Okay, what's all those Cauchy's integral formula for derivative as well. What was that formula? So f of a is equal to 1 by 2 pi I integration along c f of z by z minus a dz. That's what can be simplified as integration f of z by z minus a dz is equal to 2 pi I f of a, right? So that's what we're gonna get by Cauchy's integral formula. So here you see, now if you apply these two in this term and this term, then what we're gonna have? Integration along c1 f w by w minus z dw. Here compare dw with dz, fw with fz, and c is compared to c1, then a will be compared to z. Instead of a we have z, instead of z we have w. That's the difference. Okay, so then it should give us 2 pi I f of, instead of a we have now z. Okay, so that's what we're gonna have, right? So that's therefore, so just wait, equation number 2. So first term, this gonna be equal to this one, right? So what we have got, 2 pi I, just wait, okay, now let us evaluate this one as well. Integration along c1 f of w by w minus a dw, that's going to be equal to, here if you compare this one with this, instead of z we have w, and instead of a we have a here, right? Nothing to worry about that. So then it's going to be 2 pi I f of a, right? We're going to get this f of a. Now let us apply this one, and now let us apply this theorem here. So here, which one going to be applied, which theorem should be applied here? Now here we have square. Okay, so here we're going to use Cauchy's integral formula for derivative. What was that term? So now just wait, we don't need this first part, just let me cut this one, just keep it here. You can write this formula directly as well. Okay, now Cauchy's integral formula for derivative. Now let me adjust these two terms in order to find space. So here, now you see, what was the theorem for nth order derivative? The theorem was something like this. The Cauchy's integral theorem for nth order derivative. Nth order derivative of function f at z is equal to a is equal to n factorial divided by 2 pi I integration along c f of z divided by z minus a whole to the power n plus 1 dz, right? So we can write this theorem in this form as well. So you can write this way. If you want to evaluate this integral, then what you're gonna get, you can write this theorem in this form as well. Just wait, let me you can evaluate this integral using this theorem is equal to 2 pi I by factorial n, right, by factorial n into f nth order derivative of f at z is equal to a. You can write this way. So hope you have understood this, right? So now let us apply this one here in the third term. So as you can see, we have here this is square. So here we're going to apply this derivative integral formula for derivative, right? So here we have second order derivative. So what going to be the result in this case? What we're going to get now, integration along c1 fw by w minus a whole square. So here we have whole square, so we can here this n plus 1 is 2. That's why n will be equal to 1 in this case. So that's why what we're gonna get 2 pi I by factorial 1. Factorial 1 is nothing but 1 f to the nth order derivative of f. Here it gonna be first order derivative of f at, here a is not this a simply, so you can write a. Okay, so you will get this result. So similarly you can evaluate this one as well, this theorem, this term, this part along c1. So integration along c1 f of w by you have w minus a whole cube. So here n plus 1 is equal to 3, so n gonna be equal to 2. So in this case we're gonna get 2 pi I by 2 factorial. We get 2 factorial f. Here we're gonna get second order derivative as n is equal to 2 here at z is equal to here not z, w is equal to a. That means at the point a, right? So that's how we're gonna get, right? Similarly here this is gonna be equal to this one, integration along c1 fw by w minus a whole to the power n plus 1 is equal to sorry, I forgot to write dw here. Let me write here dw. So here also dw. Okay, and that's gonna be equal to just wait, let me adjust these things a little bit more. Okay, so here you see this is going to be equal to 2 pi I by n factorial nth order derivative at a. That's what we're going to get. Now let us use this value in equation number 2. Okay, so we're going to replace this. Now let us use this results in equation number 2. Okay, so here you see let me clean these things, just wait. So this is going to be replaced by this result. Here you can see, right? And this second term, this is going to be replaced by this one. This is going to be here, this is going to be equal to this one, 2 pi I f of a, right? And here this part, I'm not talking about this. So z, here we're going to get z minus a into, instead of this we're going to put this value. Here you can see 2 pi I by factorial 1 f dash of a, right? And similarly in the next term we're going to get z minus a whole square into, instead of this we're going to put this value, right? So hope you have understood. Similarly, this one into, instead of this, we're gonna put this, right? So if we do so, then what we're gonna give it? So using these results, so here you see what we can write. Using these results in equation number 2, we get what we get. Let me go to the next slide. So here we're gonna have 2 pi I f of a plus 2 pi I f of a plus z minus a 2 pi I f dash of a plus, just wait here, okay, 2 pi I first order derivative of f at the point a. Similarly, z minus a whole square 2 pi I by factorial 2 here. So here we had factorial 1. Factorial 1 means 1. So if you don't write, then also okay, that is no problem there. Okay, there is no problem. So second order derivative of a at a, right? Second order derivative of f at a. So similarly, dot so on, we're gonna get z minus a whole to the power n 2 pi I by factorial n. Here we have nth order derivative at the point a, right? That's what we're gonna get. So hope you have understood how we have got this. So let me tell you again. So what we have done here, so let me clean these things, just wait. So let me explain it again, how I have got this step. So what we have done, those results here, you can see those results of this integral I have evaluated here using these two theorem by Cauchy's integral formula and Cauchy's integral formula for derivative. These results are used in this equation number 2. So here this part is replaced by this result because this is equal to this one, right? So we have put this one here. Similarly, this integral is equal to this one, right? So I have put this one here, okay? And this part here, you can see this integral is equal to this one, right? Here you can see clearly this is the same integral, right? So this is put here, and putting this, what we have got? We have got this, right? So here you can see this is replaced by this one, this one. This is the result into this, right? So that's how we have done. So hope you have understood this. So just wait. So that's how we have got this result. So here 2 pi I, 2 pi I, 2 pi I, 2 pi I, 2 pi I cancels, right? And then what we're gonna have here, so we're gonna get f of a is equal to it's supposed to be f of z, I think, right? So here you see, so here we have w minus z, so here f of z, so this is supposed to be f of z, right? So here this is f of z, right? So then f of a, then plus z minus a into, here we have first order derivative of f at the point a plus then z minus a whole square by factorial 2, second order derivative at a, then plus dot 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 plus z minus a whole to the power n by factorial n, nth order derivative, right? Nth order derivative of a. So that's what we have got, right? So hope you have understood, and this is the Taylor series proved. So here you see, let me go to the series first statement. This is the series, right? So just I have written this series in this way. So here you can see this is the only difference here. So I have written this here, you see, so I have written this one here and this one here. That is the only difference. You can write this way also if you want. Just wait, let me cut these things. Okay, let me copy this result as well. So here you see this result can be written this way as well if you want. Okay, just write this one here and this one here, change the place. Okay, that's what you can do, and that's how we have. This is the Taylor series. So hope you have understood this. So in the next video we're gonna solve a few problems from HK's mathematical physics books, okay, based on this Taylor series. Okay, so see you in the next video. Thank you for watching. Take care.